Dear colleagues and friends, it's an honor and a pleasure for me to speak at this year's SMRA 2020, even if it's just in a virtual world. And I want to thank the organizer, specifically Richard Frayne, for inviting me to be part of this distinguished faculty. I will talk about MRI of the heart-brain axis. Before I do so, I want to disclose potential conflicts of interest. I'm involved in software development and receive research support and also personal support from several sources, as you can see here. Cardiovascular risk and disease is a key factor in our healthcare world. Cardiovascular disease is a key driver of morbidity, mortality in most countries, especially also in emerging countries such as India, China, South America, or countries in South America. And aging and lifestyle choices increase this burden and also the associated cost. Now, preventing cardiovascular disease has been on the agenda since many years, but we all know, definitely most of us by personal experience, lifestyle changes are hard, especially referring to nutrition and physical activity. Primordial prevention, so not start preventing if people already have risk factors, but preventing risk is not yet a successful endeavor. There is an attempt to get better at that by a truly personalized approach, but this is limited currently by a lack of understanding of the interplay between various risks. So what is the role of environment and nutrition and lifestyle in certain populations with a certain ethnic background, with a certain genomic background? So there's a lot to learn. And in an attempt to understand more about that, Sonia Anand, Jack Tu, and I, almost 10 years ago, embarked on the endeavor of the Canadian Alliance for Healthy Hearts and Minds cohort study. It is a study that was performed in close to 9,000 healthy participants aged 35 to 69. And we wanted to understand the role of socioeconomical and socio-environmental factors such as living environment, built environment, personal lifestyle choices and such on individual risk factors, subclinical disease, and also events. We also wanted to identify patterns of contextual factors, risk, health service utilization, and clinical outcomes in high-risk groups. And last not least, to identify markers of early subclinical dysfunction in the brain and the heart, and also with understanding and describing their relationship to individual and contextual risk factors and outcome. Now, currently, the Canadian Alliance does not have follow-up data, but we have already a couple of data, and I want to share with you a few of them. So in the brain, what was interesting, and we published that last year, was that compared with the Interheart risk score, which is a completely blood-free and easy to acquire risk score based on smoking habits and lifestyle choices and a few other markers. What we found is that compared to the overall population, there was a higher in patients with a higher risk score, so moderate or high risk, there was a higher incidence of MRI findings, specifically silent brain infarcts, and thus that was true for lacunar and non-lacunar infarcts, and overall MRI detected cerebral vascular disease. So this is just to get started. So here we could show that risk factors such as, and in fact, the data were very similar for the Framingham risk score. So we know that these risks, the overall risk is associated with more cerebrovascular disease that can be detected by MRI in a general healthy population. And I should mention here that the CALM, so the Canadian Alliance population, was relatively healthy relatively well educated and relatively young. So we're not talking about elderly people or people with particularly bad lifestyle habits. Now, to further expand on that, we also looked at the relationship between those findings in the MR and function. And of course, in the brain here, we talk about cognitive function. And that's a paper that was published this year in Stroke. And what we found here in this analysis was that the MRI findings in the brain indicating injury is indeed associated with a worse performance in cognitive function tests. So the MoCA was one of them, and here these are the results of the DSST. And you see that with the number of silent infarcts, the performance, the average performance in these tests drops. So that is also, that seems pretty obvious, but it actually has not been demonstrated so far in a larger population. So also in this paper here in a little bit more detail, so here the DSST and here the MoCA, and you see that white matter lesions, non-lacunar stroke, and more extensive injury all were associated with a drop of the mean performance in, especially in the DSST. In the MoCA, this was not found in white matter lesions and non-lacunar stroke, but that's probably because the MoCA test is itself not as, let's say, as detailed or not as sensitive to changes of cognitive function as the DSST. So, another very important component of looking at cardiovascular risk, and especially when looking at primordial prevention, is to understand vascular dysfunction that is before events. So we want to have a better understanding of how risk factors and which risk factors could early affect vascular function and thereby basically be the canary in the coal mine. Technique we have applied in Montreal and before when I was in Calgary is using bold sensitive MRI. And I will not talk too much about the bold effect. You probably know that all. And I will also just briefly mention the landmark paper by Ogawa and others to show that oxygenation sensitive MR can be used to identify very small changes of oxygenation in the brain associated with brain activity, and that laid the ground for functional MRI of the brain. Now, many years ago, I have applied that when I was in Berlin. We have applied that in patients with coronary artery disease and could indeed show that this type of imaging, so oxygenation sensitive imaging, can be used to identify coronary artery stenosis. And this is work from Calgary, where we could show that this stress test using adenosine and oxygenation reserve can identify patients that have a significant coronary artery disease using fractional flow reserve as the current accepted gold standard. But what we also observed was something very interesting. People holding their breath, and these here are, this is work also that we performed at the Stevenson CMR Center in Calgary. The longer these athletes could hold their breath, there was actually a net increase of the signal intensity reflecting an increased oxygenation, whereas the opposite was true if they hyperventilated. So, and we could show in experimental studies that indeed a change of carbon dioxide triggers vascular dilatation in the heart. That has been known before, but we could visualize that basically live in MR. And this, we also showed that this happens in the brain. And it's also well known in the brain world that hyperventilation is a trigger. So here is an overview of the physiology. So hyperventilation leads to vasoconstriction and breatho to vasodilation. So such breathing maneuvers could serve as a kind of a stress test or a vascular trigger for diagnostic testing. And indeed, we have applied that. This is just one of the papers. This was performed in a pig model where we could demonstrate that. And now, interestingly, this is work from very recent work from Montreal. We could also show that if you do that in the brain, we call this the core, so the cerebral oxygenation reserve, we could show that the so-called core, so the vascular response, is reduced in patients with heart failure. And that was parallel to the myocardial oxygenation reserve. So there is a parallel response, and this is not surprising. We know that the heart and the brain act in parallel in cardiovascular disease. So where are the gaps of understanding? And I would just want to give one example. So it has been long known that anxiety triggers an unfavorable response of the vasculature, and this is data from the heart, where an increase of the stress response in the brain was associated with an increase of contractility when it was associated with anxiety. Now, anxiety plays a huge role in our society. So could anxiety trigger cerebrovascular and also coronary vascular disease? So this is just one of the gaps we need. So let me summarize. Cardiovascular disease affects all organ systems. The heart-brain axis receives more and more attention because of similarities in impact and physiology. They both have a specific response system to breathing-induced triggers of vascular function, and I think we need a much better understanding of their intertwined physiology and associated risks. And with that, I want to thank you cordially for your attention and wish the organizers and the audience all the best, and stay safe. Thank you very much.